Hello friends, I welcome you in lecture number 45 on logic. In this lecture also we will discuss one question on rules of inference for quantified statements, and we are discussing that how we can show that given argument which involves quantified statements is valid or not. So for that we have discussed rules of inferences for quantified statements in lecture number 44. So if you have not seen that lecture, you can watch that lecture first, and then only you will be able to understand this lecture. So first we understand what is this question. Show that the premise is everyone in this discrete mathematics class has taken a course in computer science and Marla is a student in this class. Imply the conclusion Marla has taken a course in computer science. Here we are given two premises. This is first premise and this is second premise, and we have to prove that these two premises imply this conclusion, or we can say that we are asked to check whether this argument is valid or not. And you can see here everyone in this class has taken a course in computer science. So this will be involving quantifiers. Everyone in this class, this suggests that this is going to be a quantified statement, and this is a statement Marla is a student in this class. So we have to first consider some notations, and then we have to translate these premises and conclusion into symbolic form, and then we will check whether these two premises imply this conclusion or not. So what is given here, everyone in this discrete mathematics class has taken a course in computer science. So there are two things here, that everyone is in discrete mathematics class, and another thing is that they have taken a course in computer science. So they are talking about two things, that person is in discrete mathematics class and the person has taken a course in computer science. So we will use these two notations. We can denote by d of x. Suppose d of x is the notation that x is in this, I will write shortly as dm for discrete mathematics. So x is in discrete mathematics class is denoted by dx, and for course in computer science, cx denote that x has taken a course in computer science, that we shortly write as CS. And using these notations we write down our premises and conclusion. So using these notations we can write that therefore premises are, first premise is everyone in this discrete mathematics class has taken a course in computer science. So this we can rewrite as, if x is in discrete mathematics class, then x has taken a course in computer science, and that is true for all x. So we will use a universal quantifier. We can write that for all x, whenever x is in discrete mathematics class, imply that x has taken a course in computer science. So we have this conditional connective dx implies cx, and this is true for all x because it is given that everyone in this discrete mathematics class has taken a course in computer science. So we can write in this way also, that for all x, whenever x is in discrete mathematics class, x has taken a course in computer science. So that is the first premise. We have translated this premise into symbolic form. Second premise is Marla is a student in this class or in this discrete mathematics class. and we have used dx to denote that x is in this discrete mathematics class, and we want to write that Marla is a student in this class. So we will replace x by Marla and we will have d of Marla. So second premise in symbolic form is denoted as d of Marla. And what is conclusion in symbolic form? And conclusion is Marla has taken a course in computer science. X has taken a course in computer science is denoted by Cx. So if I take x equal to Marla, then I will have C of Marla denoting that Marla has taken a course in computer science. So our conclusion is C of Marla. C of Marla means here take x equal to Marla and we will have C of Marla denoting that Marla has taken a course in computer science. And here we have to prove that these two premises imply this conclusion, or we can say that we have to check that the argument with these two premises and this conclusion is valid. So for that, as usual, we start with two column proof. On one side we can write statements or steps, and on this side we will write down the reason which we are using. So first step is our first premise, which is for all x dx implies cx. For all x dx implies c of x, and that is our premise. And we want to conclude that we have to conclude that C of Marla, that is Marla has taken a course in computer science, and D of Marla is that Marla is in discrete mathematics class. So from this, if I consider x equal to Marla here, because this is true for all x, therefore I can take x equal to Marla. X equal to Marla will give me D of Marla implies C of Marla. So from this I can taking particular value of x as Marla. So this is nothing but universal instantiation. The rule of inference is universal instantiation on number 1. Now we use second premise, which is D of Marla. So let me write here D of Marla, that is premise. And now you can observe that 2 and 3 are propositions or statements, and they are in this form: P implies Q and P, and this is our familiar modus ponens. If we have P implies Q and P, then we have Q here. So if you compare here, then P is D of Marla and Q is C of Marla. Therefore, using modus ponens, here we arrive at desired conclusion. And here I have to mention that I have used rule of inference modus ponens on number 2 and 3. So we have arrived at this conclusion. So we can say that these two premises imply the conclusion Marla has taken a course in computer science. So this is very easy, and it was asked in GTU Winter 2024 exam. So be careful that you have to keep in mind that whenever we have everyone, then we will use universal quantifier, and we will have conditional statement here. Everyone in this discrete mathematics class has taken a course in computer science. So whenever we have this type of statements, then we will use universal quantifier and this type of conditional statement. And for existential quantifier we are going to use conjunction connective. Okay, if I want to write down in this way, suppose there exists x such that px and qx, that means there is some x in the given domain for which px and qx both are true. So px and qx are true for some x that we can denote in this way also. So we will continue with this type of problems in upcoming lectures. Thanks for watching.